Number 11, which of the following is a function y whose derivative is dy dx equals 2 sine of x with the initial condition of y of pi is 1. So we want to find the function that has this derivative. To do that, we need to take the antiderivative of 2 sine of x, also known as the indefinite integral of 2 sine of x dx. So that's 2. The antiderivative of the sine is the negative cosine of x plus c. If you remember the indefinite integrals, we always have to do plus c. Now, we know since y of pi equals 1, then when I plug in pi, I get out 1. Cosine of pi is negative 1. Negative 2 times negative 1 is 2. So c is going to be negative 1. So then, y of x is negative 2 cosine of x minus 1. Number 12, for x is greater than 0, dx, the derivative of the integral of ln of t cubed plus 1 dt from 0 to 2x. This is that second part of the fundamental theorem of calculus, where the answer is just going to be the ln of, substitute in 2x for t, and then multiply by the derivative of that upper bound, which would just be 2. So I get 2 ln of 2x times 2x times 2x is 8x cubed plus 1. The graph of the function shown above consists of 2 line segments and a semicircle. Let g be defined by g of x is the integral from 0 to x of f t dt. What's the value of g of 5? So up here, g of 5 would just be the integral from 0 to 5 of f of t dt. So that just wants to have us find the area from 0 to 5. So that's going to be the area of this triangle. So 1/2 base is 1, height is 3, plus the area of a semicircle. So pi times r squared, the radius is going to be 2. So 1/2 times 1 times 3 is 1.5. 2 squared is 4, divided by 2 is 2. We get the 2 pi. So 1.5 plus 2 pi. 14, which should automatically jump out at you, and it will by the time we take the exam, is this is a L'Hopital question. Now again, it's not a guarantee that it is, but the setup, the formatting of it, the two things that kind of give it away, one is the limit, the other is the quotient. Limit of a quotient, not always, but quite often is going to be a L'Hopital's rule question. So to do that, what we need to do is first of all verify that taking the limit of the top gives us 0 and the limit of the bottom is 0. So somewhere, limit as x approaches 1 of the integral of 1 to x of e to the t squared dt is the limit from 1 to 1 of e to the t squared dt. And that's 0, right? The integral from anything to itself is going to be 0. Limit as x goes to 1 of x squared minus 1. We get 0. So by L'Hopital, it's always a good idea to write y. This is going to equal the limit as x approaches 1 of the derivative of the top. We'll deal with that in a second. Derivative of the bottom, pretty straightforward. The derivative of the top, so the d dx of the top. This is that fundamental theorem of calculus, part 2. They cancel, we get e to the x squared. Limit as x goes to 1. If I plug 1 in, I get e to the 1 squared over 2 times 1. So we get e over 2. 15, the figure above shows the graph of f if f is the integral from 2 to x of g of t, which of the following could be the graph of y equals g of x. So if this is the graph of f and f is the integral, then f prime is the derivative with respect to x of 2, x of g of t, dt, fundamental theorem of calculus, part 2, we get that's just g of x. So that if you want the graph of g, all we need to do is graph the derivative. Well, derivative is slope. So this, since this is linear, the slope is going to be constant and it's positive. So we get the only positive constant function. And that takes us through 15. The next video will take us up through number 21 probably, and then we'll do the FRQ together afterwards.